Sorry guys, there was a power cut, so I'll just continue with the previous discussion. So I have stated that there are two type of transconductance amplifier discussion that we are going to do. The first case being the source, load, and the feedback network being ideal, with the basic amplifier being non-ideal, and then later a practical case which is considering everything as non-ideal case, and see how to work out the uh, the feedback impedances as well as the feedback uh, amplifiers gain and stuff. Okay, so let us begin with this basic transconductance amplifier, and let us model the non-ideal model of this basic transconductance amplifier. So since because the input to this basic amplifier is a voltage that we are trying to fetch at the input, uh, whenever we try to read a voltage inside this, ideally there should not be there is supposed to be an infinite impedance faced by this input of the basic amplifier. So we basically wanted this Ri supposed to be infinite, but under non-ideal condition, so this is an ideal case, but when I say it is a non-ideal, then what does it mean is that we supposed to end up having a finite amount of resistance, which is no more an infinite quantity, but it's a finite quantity. Okay, and similarly the output impedance of this particular network, uh, just be, just because the basic amplifier is trying to feed a current, the current source or whatever it is, it's supposed to be an infinite, but again just because of the okay, let me write this. Okay, so this is an ideal case, but in general a non-ideal condition would then having an output impedance which is RO, which is non-finite, which is non-infinite due to this non-ideal characteristics. Okay, so with that in mind, let us try to build the basic, sorry, not the basic, the feedback amplifier, having this basic amplifier being a non-ideal model, and then with the feedback network and with the voltages and the load. Okay, yeah. So let me begin with this feedback network or feedback amplifier. It's not a network, and we are trying to evaluate this AF, and we know that this AF or the feedback amplifier gain is defined as the input is basically a voltage Vs, and the output is an output current which is I naught. Okay, so I'm just feeding an input voltage of Vs rather than Vi. So this is quite different from the basic amplifier gain, where the basic amplifier gain will have a term which is Vi, and the output signal is a current which is I naught. Okay, so these two are two different quantities that we have. So right now, just because we are trying to draw the feedback amplifier, the input to this feedback amplifier is a Vs source, and so that gets connected, and since because this voltage source is an ideal one, we don't have the resistance Rs, otherwise we have to add this resistance Rs along this particular path. Okay, so right now the source and everything is considered except for the basic amplifier as non-ideal one. So as I said, the input impedance ideally is supposed to be equal to infinity, but since because we are considering a non-ideal basic amplifier, we are modeling with a resistance, a finite valued resistance of Ri. Let me write it as Ri, and then we need to convert the voltage drop across this. Okay. So whatever the drop that is happening across this resistance Ri is considered as Vi, and this Vi is sensed by a kind of voltage controlled current source, which could be written as A times that of Vi, and there is an output impedance whose value is R naught. Okay, so that is being connected in parallel to it, and then there is a load that gets connected. So hopefully I should have, I will just mark these structure which models my A circuit or the basic amplifier circuit. Um, okay, and let me write the label as Vi outside the structure. Yeah, this is what it gets in and this is what it gets out, and again we have a load which is an ideal one, the load is again an ideal, so due to which it is a short circuited, and yeah, so this is what we have basically. And right now we need a feedback network that samples an current. Okay, so the way the current can be sampled is by thinking of an ammeter, wherein the current has to be sensed along the wire, okay, rather than a voltage where you will be sensing a voltage across two wires. In this case, when you sense a current, you have to pass through the current through the wire that flows. Okay, so which means that we need to tap the current flow in a kind of series connection at the output, and then pass it through an ideal structure. So make this current to short it. Okay, so there is no drop that is happening here, and this flow of current, which is basically I naught. Let me just use a color. So basically the current I naught is gets in, and that goes something like this and flows and comes out something like this. Okay, so I have a current that has been flowing here, and we need a transformation done by this beta network, and that beta network is supposed to sense in this input current for this beta network, which is I naught, and convert this beta like current I naught into a fraction of a voltage, or a beta times that of the current into a voltage. Okay, so let me just complete the structure. What we needed is an inverse transformation of this thing. Okay, so what I had for a basic amplifier is something like a voltage controlled current source, but right now we need a beta network that performs exactly an opposite. So which means that we need current controlled voltage source. Okay, so that has been modeled with the beta times that of the current, because the current is the one that has been sensed by the beta network and converts in terms of a voltage. Okay, so the output that is provided here is a voltage, and we call that voltage as Vf, and that has been fed in series with this, or has been mixed in series. Okay. Yeah, so hope that this entire structure is clear, and let me just try to encapsulate our beta network with this box in blue, and this is our beta network or beta circuit. Okay, so this is all the ideal case, and with this ideal case across the source as well as the beta network, one thing that we need to see here is that we have to ensure that the input impedance and the output impedance will get a specific value when we have a non-ideal component inside our basic amplifier. So this is what will be evaluating through this throughout this particular ideal case structure. So now I just want to step down this structure into a very simple feedback amplifier. Okay, so with the notation that the input is fed as a voltage source Vs. Okay, and this is again a feedback network, but it's modeled as a two-port network. Okay, and the input impedance seen by this voltage source Vs is read as RIF. Okay, and we will have something known as a voltage controlled current source, but the gain through this medium is AF, that is the feedback gains times that of the voltage source Vs, that is seen by this RIF, and the output impedance would then be modeled as ROF, and the load to this would be a short circuit. Okay, and the current flow is given by this I naught. Okay, yeah. So hope that this is the simplified version of the basic the feedback amplifier. Let me write this simplified version of the feedback amplifier, okay, or the equivalent circuit of a feedback amplifier. Yeah. So now that let us try to come up to the real calculation of RIF and ROF. Okay, so now that we need to figure out these expressions, and one can directly use this knowledge that we have gained from our voltage amplifier, that whenever we have the type of, like, depending on the type of feedback network connections that we have across the input and output, one can immediately compute the value of the output impedance of the feedback network in terms of the open loop impedances. So So in the case of an input, we could see that let me use, yeah. So there is a series connection. Okay, the type of feedback that I am using is a series connection, and even at the output, the type of feedback that we are using is a series connection. So whenever we have the series connection, generally the RIF and this ROF will be a magnified version of the RI and RO. So where RI and RO are the input and output impedance of the open loop or the basic amplifier input impedances. Okay, so magnified by the factor of 1 plus A beta. So now the whole point is that I will just try to prove this particular quantity, but in general we no need to prove each and every time when we try to solve it. Okay, so depending on the connection, one has to quickly write down this these expressions whenever we have a series connection, whereas whenever you have a shunt type of connection, then one could write it as the diminished version of this input and output impedance of the basic amplifiers. Okay, yeah, so hope that you are clear, but just for time being I'll just try to prove this particular statement, and after then we won't be doing any kind of proofing for each and every type of connections that the feedback networks makes with the feedback amplifier. Okay, so let me try to prove that the statement that I have made, the input resistance of the feedback amplifier, which is modeled as RIF. Okay, yeah. So since because of the series connection that we have across this input for mixing, one could see that the voltage Vi is basically gets diminished. Okay, so this particular quantity is getting reduced just because of this feedback voltage of Vf that is trying to mix along with the Vs, so that the voltage across this Vi is being reduced. Okay, so one could model this reduction in the voltage of Vi as Vs divided by 1 plus A beta. So again one could go through this particular circuit model to get down to the simple expression. Okay, so I'm not proving it, but in case if you want to prove, you can just write it as so Vs we know it is a summation of Vi plus Vf, and one could write this Vf in terms of what is known as beta times that of I naught. Okay, so that is actually what we have, and again one could rewrite this I naught terms of gain times that of Vi, right. So okay, so pulling out this term Vi in common will end up having this quantity as Vs, and from here one could write this quantity as Vi equals to Vs divided by 1 plus A beta. So it's just the proof one can quickly write down rather than doing all those calculations. Yeah, so now that we have this as our input impedance, and the next thing is that we need to compute the impedance posed by this feedback network, the input impedance. So we know that the input impedance can be evaluated from by looking at this particular quantity. Okay, so there is a current flow, and the current that is flowing inside this feedback amplifier is the II. So and the voltage that we have across the input of this V, like the voltage or the source signal that we are feeding to the feedback amplifier is basically Vs. Okay, so the ratio of this Vs divided by the current should give us the value of this RIF. Okay, and with that let us try to evaluate the quantity of RIF. So RIF is defined as Vs divided by II, and one could write this Vs using this equation, and that would end up having Vi into 1 plus A beta divided by II. Again the ratio of this Vi divided by II could be taken out from this particular quantity. Okay, So when we look carefully into this yellow box, which is nothing but the A circuit box, the input is basically a voltage and the current that flows inside the circuit is II. Okay. Now the ratio of this Vi divided by II is nothing but the Ri component. Okay. So using that relation, one could re-express this Vi divided by II as something like Ri. Okay. So it is a magnified version. So the this is the feedback impedance, input impedance or in the input resistance, and the R naught sorry, the Ri is nothing but the basic amplifier or transconductance amplifier input resistance, and that is being magnified in general whenever we have a series connection. Okay. So this is something that we always have to remember, this one, and there is one more quantity that will be finding out when we discuss about the practical case. So those are the two things that we always have to remember while doing the computation. Okay. Yeah. So having found this, right now let us try to write the expression for the output resistance, which is ROF. Okay. Yeah. So now in order to compute the output resistance, we generally have to kill this connection. So what I uh, there are two major steps that we always perform. The very first step is to kill any independent source or any input independent source. So in this case, an input independent input source is nothing but the Vs, so that has to be killed. Okay. This is the very first thing that we need to do. The second one is to apply Vx and measure Ix to get the value of it. Okay. So again, all of these exercises are just to make you to familiar with this particular flow, but otherwise we no need to do all these derivations. Just by looking at the type of connection, one could directly write the value of ROF and RIF. Okay. Yeah. So let me just pick this particular component, copy this circuit. Yeah. So the way that I can kill this input voltage source is by shorting this Vs to the ground, right. So let me do that. So let me just try to kill this guy Vs with a short circuit, and then what we are supposed to do is to apply um, I guess it is something like we have to apply a current. Yeah. So in this case, since because we are dealing with a current at the output, you have to apply Ix and measure for Vx. Okay. Yeah. So in that case, let me try to apply a current Ix, okay, and then measure for the value of the drop across this particular component as Vx, okay, across the Ix as Vx. So now that let us try to do this. So now clearly one could see that whenever we short this particular input V naught, sorry, Vs to the ground, we end up having a value of Vi that is equal to minus of Vf. Okay, and this is from the input side is what we have, and again one could write this Vf as a product of beta times that of I naught. So we have a Vi in terms of defined in terms of I naught. Okay. Now let us try to write the expression of ROF. Okay. So ROF is something defined as Vx divided by Ix, and the value of Vi is returned as beta times that of I naught. So the current that is flowing in this circuit I naught is equal to the value of Ix, right, because we are pumping in a current, we are forcing a current, and that is the current that flows through this beta network as well. So instead of writing it as I naught, I can rewrite it as Ix. Okay, yeah. So now the total current, or basically the drop across the resistor will give us the value of Vx, right. So Vx is generally measured as a drop across resistance. So in order to know the drop across the resistance R naught, we need to know what currents are flowing through this particular circuit, right. So in doing so, one could see that there is a current that is looping, which is defined as A naught times, sorry, A times that of Vi. The other current is the current Ix that has been pumped in the place of I naught. Okay. So these are the two currents that are flowing in opposite direction, and the difference in these two currents will give us the total current that flows through the R naught. Okay. So let me write that as Vx is equal to Ix that is flowing minus the gain times that of Vi is the total current, and that is flowing across this R naught. Okay. So now I need to replace this Vi in terms of Ix. So which means that we end up having something like A beta Ix R naught, and that is our Vx. So Vx divided by Ix will then become Ro and Rof. Okay. So hope that it is again been proved that whenever there is a series connection at the output, one would end up having an increase in the magnitude of the output impedances or the input impedances depending on the type of connection alone. Okay. Yeah. So with this proof, let us move on to the practical case where everything what we have would be in non-ideal conditions. So in that case, we call it as practical case, and let me just quickly model this practical case, and then maybe let me try to paste the circuit that I had. Yeah. So now that let us try to introduce the non-ideal Cara into this particular picture. Yeah. So first let us try to bring the non-ideal model of our voltage source Vs. Okay. So that is nothing but including a resistance will do this particular job. So let me just try to add an impedance Rs. Okay. And also the load supposed to be a non-ideal. So which means that in the place of a short circuit, I have to add a resistive load. In the place of 0, we have a finite valued load. Okay. And there is again a feedback network. Even that feedback network has to be modeled as a non-ideal model. So the way that could be modeled is by looking at the type of connection that we make, and it is something that we have already discussed. So it is nothing but the Z parameter two port model will try to have this kind of behavior. So let me just try to model them. So it would be like Z11, and in the place of beta times I naught, what we have is equivalently could be written as Z12 times that of I2, and again in the place of a short circuit we have the same similar kind of setup where we have an impedance, and that value of impedance is Z22, and we again have this being modeled as a voltage, sorry, as a current controlled voltage source. Okay. Yeah. So hope that it is clear how one could model this as we have discussed in the previous session. And whenever there is a series connection, what we generally wanted is some sort of Thevenin's representation. So both at the input as well as the output, we have this series connection, and they have been represented by some sort of Thevenin's representation as a kind of voltage source in series with a resistance, and that is what we have used here. And that particular model we call it as a um, a Z parameter model. Okay, two port model. Okay, yeah. So now having this model, let us try to bring out the ways by which one could like now let us try to clean up this particular entire structure by pushing all those non-idealities from the sources, from the load as well as from the beta network, and pushing all these non-idealities into the A amplifier, okay, or the basic amplifier. So the way that one could do is by again yeah, so with some sort of assumptions. So we will start with the assumption that the factor Z21, which is the reverse transformation, is assumed to be equal to 0. Okay, so we always have this particular relation, and uh, so in turn this defines the Z21 times that of I1, which is a voltage, which is a current controlled voltage source, to be equal to 0. Okay, so since because this represents a voltage, having a voltage to be equal to 0 is nothing but it's modeled as a short circuit. Okay, so this is the first assumption that we make before we commit ourselves to push all these impedances to the other part, and now let us try to draw the model again. Yeah, so in this case one could move the source resistance into this amplifier, so that the source right now is modeled as a kind of ideal model. So again one could push the load into this basic amplifier RL, so that right now the load has become an ideal, and similarly one could push the value of Z11 into the basic amplifier, so that the beta network is right now clean without or basically it is said to be an ideal one. Okay, yeah. So having modeled all of these things, we end up having this structure, and now let me just pick only the yellow colored structure, which is nothing but it represents the complete basic amplifier. So let me use this color in order to represent that. So the input to this basic amplifier is again Vi. So let me just model it, an equivalent model of this basic amplifier, including all the non-ideal characteristics into the basic amplifier with Ri, and here being Z11, and we have A times that of Vi. Now in this case right now this is no more equal to Vi, okay, just because it will sense only the drop across this Ri as a voltage controlled uh, current source. So if I label this one as VID, then I have to rewrite this expression as A times that of VID. Clear? Yeah. So and after then we have this impedances of R naught, RL, and then Z22. Okay. So everything is being included in this particular model, and since because they are all been shorted, what I really mean is that something like this is what we have. Okay, yeah. So this is the equivalent circuit of basic transconductance amplifier. Okay. Yeah. So now let us try to figure out the ways by which one could get the values of Z11 and Z22 as well as the value of this beta. Okay. Now the way that one could evaluate, yeah. I forgot to mention few more quantities here. The other quantities that we are about to find is this Ri, which is the input impedance of the basic amplifier, and the output impedance, which is basically can be mapped here, okay, which is RO. So do not get confused that somewhere I am tapping and then I am trying to visualize that as a kind of impedance, but never the matter. We will use this all rules that we have learned, like kill the independent source and then try to find out the current flow in order to find the value of impedances. Okay, so 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 probably we'll be fixing the value of Ix in this short circuit path. Okay, so in this particular path, Ix, and then measure the drop across the impedance to measure uh, the impedance of R naught. Okay, so that is what you are going to do, and I am just fixing a particular spot, something like this. Okay, so nevertheless, so now that we have this as our basic transconductance amplifier, now that we just move on to the beta network, and so again, in order to talk about the impedances of Z11 and Z22 connection, there are two ways by which I could evaluate these quantities. Either by using the Z parameter model, I can quickly get down to this, but one has to remember uh, about 4 different type of network connections that one could use to model the type of beta network that is used for the feedback. Okay, so that is a bit harder procedure, but there is also the other way of evaluating these impedances out of this beta network. That is the type of connection that it makes across port number 1 and across port number 2. Just by looking at the type of connections that we have, one could quickly evaluate the other ports impedances based on the type of connections that we have made. Okay, so which means that say for example, while evaluating the Z11 parameter, and if this is a beta network, we do not know what is this beta network or what type of element that we have inside this beta circuit, but while evaluating this, the other end of the port, which is the port number 2, and let me model this as 1 with a circle as port 1 and the other port as 2 with a circle as port 2. Now while evaluating the Z11, and since because this second port is making a series connection, we have to open circuit. Okay, so a series connection will always open circuit either at the input or output, does not matter. Okay, so now since because it is a open circuited, then one could apply the value of Vx and measure the Ix, so that the ratio of Vx by x should give us the value of this Z11. Okay, so it is a pretty simple process, and the same thing applies even for the calculation of Z22. Okay, so while computing the factor of like the impedance of Z22, one has to see what type of connection that port 1 is making with the feedback with the basic amplifier, or what type of mixing that we are doing actually. So again, when we look carefully, the type of mixing that we are doing is again a series. So whenever there is a series that is being made across the other end of the port, okay, then we will open circuit this particular structure. So open circuit whenever there is a series in port 1 while computing the port 2 impedance. Okay, and then again by the process of applying this Vx and the current flow, one could evaluate the factor of Z22. Okay, so that is how we can find these parameters. Now in order to evaluate the factor of beta, we know that the beta network samples in a current and it spits out a voltage Vf. Okay, so based on this one could apply a current. Okay, and let us model that current as either as I naught itself, does not matter. Okay, so just try to apply this I naught at the port number 2 and measure the voltage across uh, the port 1, so that the ratio of these two things will give us the value of beta. So beta is defined as something like an input is basically an I naught and the output is a voltage Vf. Okay, so that should give us the uh, beta factor. Yeah, so Now with these things in our mind, right now let us try to quickly talk about the other impedances. So as said earlier, uh, apart from this RIF, there is also one more impedance, which is RN. Both both the impedances are the input resistances of a feedback network, but the way the feedback amplifier, to be frank, yeah, the way that these two impedances differ by each other is that this Rn excludes the source impedance Rs, okay, and similarly the output resistance of a feedback amplifier can be written as, there are two parameters again, either as ROUT or ROF. So in the case of the only difference between these two ROF and ROUT is that this guy ROUT excludes the load impedance. So that's the only difference. Okay. So in this case, as you could able to see that the Ri value of this basic amplifier, okay, is nothing but the series combination of Rs plus Ri plus Z11. Okay. So whereas the output impedance, when you try to kill this input source, so what basically happens is that this component becomes an open circuit, and because of this all of these impedances will go in series. So which means that I would have this RO defined as RN, R naught and Z22. Okay. Yeah. So hope that it is all clear. I will make these quantities more sensible while we do a particular example problem. So probably I might extend the class uh, till we complete this particular problem. Okay. So, so determine the closed loop. CL stands for closed loop gain, which is defined as AF as I naught by Vs, and the input resistance Rn. So again the input resistance is with respect to feedback, okay, and the output resistance R out. Okay. And also there are few things that we need to assume for this network. Um, has a finite input resistance as RID, and so also assume two more conditions. RID is much larger than the value of RS as well as RF, and the RO1 is again much larger than the RF and RL. Okay. So let us use these conditions and let us look for the circuit first of all. Let me just put the structure here. So there is an amplifier with a gain of A1, followed by this there is kind of CS structure, okay, which is made of Q2 along with some load. So that load is modeled as RL, and there is an RF, and there is a feedback that connects between these two impedances of RL and RF. Okay, yeah. So also there is a voltage which is Vs and Rs here. So Now let us try to figure out where exactly the feedback network and where to identify the value of RIF and ROF as well as RIN and ROUT. Okay. So now uh, what type of sampling is being done, that is what the very first thing that we need to identify here. Now in this case, as you could see that I am not sampling a voltage here. Now how did I get to know this particular quantity is by looking at the load resistance. Now in this case, as you could see that the load impedance is connected between the drain of Q2 as well as the output is sampled uh, at the other end of the load impedance. It clearly says that whatever I am sampling is a current. Okay. So say for example, if I do not have this structure, let me just this is just for the demonstration, just to show uh, if I have some other type of connection. Say for example, I have this and there is a load RL and then there is a resistance something like this. Okay. Yeah. So let me just sample here with A1 then fit here and you have a connection something like this. Okay. So in that case uh, we are actually sampling a voltage. So this connection actually makes a sample of a voltage. Okay. But whereas here the case is that we are not sampling at the head of the load resistance, but rather we are sampling at the tail of this load resistance. So whenever we are trying to sample at the tail, what would happen is that we are trying to sample a current rather than a voltage. Okay. So in this case we are sampling at the head of the load, and due to which it can be said that we are actually sampling a voltage. Okay. So we will understand a lot about these things when we talk about the other type of amplifiers in the later session. Okay. So as of now what we are sampling is basically a current, and that current that flows in this network is I naught. Okay. So again one could use an ammeter over here just across a single wire and then measure the current as I naught. Yeah. So having done all these things, let us try to figure out the impedances. Okay. So the impedances that I am seeing here, which includes the RS, is written as RIF, and the excluding this RS will give us the factor of Rn. Okay. And similarly ROF is defined at this particular junction just by applying a current Ix in the place of I naught and then trying to measure the drop. Okay. So let us try to do that problem and then get back to this. So first let us try to convert the circuit, the closed loop feedback amplifier circuit, into the A circuit, which is the basic amplifier circuit, by pushing all those non-ideal structures into the basic amplifier itself. Okay. So now in a way, first let us try to identify where is our feedback network. Okay. So the feedback network RF alone acts as a kind of uh, beta network. Okay. So this is our beta circuit, and the input is a current. Okay. So whatever I have is a current flow, because I naught has to loop through this particular path, and whenever it tries to move through this way, we assume that the input impedance is quite larger. Okay. The RID value is quite larger, and due to which we assume that the I naught is almost closer to a value of 0. Okay. So all of the current right now flows through the RF resistance, and the voltage drop across this resistance is measured as a kind of let me use, yeah, the drop is measured as Vf, and one could see that this voltage Vf goes in series with Vi. Okay. So hope that the circuit makes sense, and now with that sense let us try to find out the R11 and R22 out of the beta network and try to push all other impedances towards the basic amplifier, and then try to find the factor of A, and once we find the factor of A as well as beta, then we can quickly step down to the other uh, findings. So let me write it as the solution. So the beta circuit, and with respect to beta circuit we need to find the value of beta as well as the input impedance of R11 or Z11 as well as Z22 or R22. Okay, yeah. So my basic beta network is just the impedance of RF, and it has port 1 and port 2, and one could evaluate this impedance of R11 by, since because this port 2 is making a series connection, um, we know that it has to be open circuited. So we end up having this as RF, and similarly the resistance R22, while trying to compute the resistance R22, we have to open circuit the other port. Okay, so here it's supposed to be open circuit the port 2, and here we have to open circuit the port 1, and we end up having the same value of RF. Okay, so now, so with these identifications, and let us also try to evaluate the factor of beta. Now we know that the factor of beta is something like RF we have, and the current that is flowing through the circuit is modeled uh, as I naught. Okay, and this current I naught, when it flows through those resistance RF, it creates a voltage Vf. Okay, so we know that the factor or we can write this output voltage Vf is I naught times that of RF, and Vf divided by I naught is nothing but is equal to Rf, and that is equal to the uh, beta. Okay, so it's a quite straightforward relation is what we have currently, and we found all the important parameters that are required to build the A circuit or the basic amplifier circuit. So now let us try to model that, and so basically the input to this A amplifier is basically Vi. So let me begin with that, and we have pushed our source resistance Rs into it, and we also said that there is that the basic amplifier A1 has a finite input impedance, and that value of finite impedance is considered to be RID. Okay, and it also has a finite output impedance of RO1. So in the place of this A1 amplifier, what we have is RID, and there is something known as a voltage controlled current source, so which I model here as something like A1 times that of the drop across this resistance. Okay, let me just draw that. I call this drop across the resistance RID as VID times that of A. Okay, yeah. And again we have this resistance RF coming out from the port 1 of feedback network, and that has been pushed onto this A network, and we have this output impedance RO1, and this is the box that we have in the place of A1. Okay, so this entire model is modeling this A1 structure, and we know that this is going and getting connected to the gate input of our Q2 amplifier, sorry, Q2 structure. So let me just model this one as VGS. So we know that the source is connected to the VDD because it's a PMOS, and let me model with this kind of structure. So one could write it as GM2 times that of VGS2, and we also assume that there is a kind of output impedance which is RO2. Okay, and at the bottom what we have is a resistance RL, right. Now this resistance RL goes in series with the resistance of RF because of this R22 quantity. Okay, yeah. So hope that everything makes sense, and hope we are doing in a very right way. Okay, yeah. So let me just try to redraw this particular structure in a very neat way, just because it might make you to confuse. So I'll just try to redraw this structure. So as we had before, we have this VGS2, let me model it properly, okay, with respect to the ground, and rather than putting the current in the top direction, I have just put them in a downward direction, okay. That is the only thing, which is GM2, VGS2, and then there was RO2 that appeared in parallel, okay. And then we have the series resistance of RL and RF, okay. So hope that right now this particular circuit is clear, and this is directly taken out from this combination, and let me model this ROF identification point as something like this. Yeah, and this is the spot at which I will try to identify the value of RO, and this would be the spot at which I will identify the value of RI, okay. Yeah, so first let us try to begin identifying the value of this A. So the factor of A has to be computed. Um, First of all, let me label this one as something like yeah, VO1. Let us assume it as VO1, or rather than VO1. Okay. Yeah. So we know that the capital A of this entire circuit can be defined as I naught divided by Vi. So we have to break this relation using the chain rule. Say for example, first we need to identify the relation between this Vi to this Vid. So I am using a simple chain rule, and from Vid to VGS2, and again using this VGS2 with respect to the factor of I naught, okay. So it's a pretty simple straightforward rule, and right now this equation becomes much more simpler just by analyzing each individual terms separately. So the first term, the relation between this Vi to Vid, is a simple basic structure that one could read from this green colored structure, so it's which is a voltage division rule. So it becomes something like RID divided by uh, the series combination of RS, RF, and RID. So we got the first term, and let me use a different color, the second one, which is the relation between this VID and VGS2. So that could be spotted from this relation. So we know that the product of these two quantities of A1 times that of VID generally results in an output voltage which is written as VGS2, right. So in short, what I have is VGS2 is nothing but A1 times that of VID, and it never no need to consider the factor of RO1 that is associated with this particular component, okay. So what we really mean is that this ratio ends up having a value of A1. Yeah, I think I forgot one important quantity out of this is the computation of this VID. Now, since because we are feeding, yeah, since because the Vs is a positive potential and that is fed to a negative potential here, the way that Vi has to be returned is in the other way. Okay, yeah, I think this is fine. Over here, it has to be changed in the inverse direction. I think I think guys this is considered as a voltage amplifier. The A1, I forgot to mention that the A1 is a voltage amplifier, okay. So with that consideration only we have to draw. So due to which what we have is a voltage controlled voltage source here, okay, and the voltage drop across this RA is supposed to give us this, and since because the negative terminal is being fed here, the drop is considered as minus at the top and a negative positive sign at the bottom of this VID, and that in turn should have uh, a voltage source in series with an output impedance of RO1. Okay, so I wrongly modeled this structure at the beginning. Okay, because whenever we have an op amp, it is always considered to be as a voltage amplifier. But here in this case, the combination of this op amp A1 along with Q2 is what it makes as a kind of transconductance amplifier. Okay, so sorry for that. I really didn't tell about this. Okay, yeah. So this has been modeled as voltage, and since because the Vi goes to the negative or to the negative polarity of this basic amplifier A1, okay, we are feeding it as a minus sign at the top and a positive sign at the bottom. Okay, yeah. So hope that you are not getting confused, and due to which there is a small change that I have to add up as expression of VID by Vi, which is a negative sign. Okay, so there is an associated negative sign along with this ratio here, and later on what we have is the gain of A1, and later on now we will try to identify this expression of I naught. Okay, now so in general the value of I naught is nothing but the current that flows into the circuit, which has been modeled as something like this. Okay, yeah. So with that, let us try to evaluate the current. Okay, so the current that flows here, okay, through this RL RF combination is what we have to write it. So now the way that this could be modeled is by making use of this current division rule, which states that minus GM2 times that of VGS2, okay, is the current, and I hope everyone is familiar with this current division rule. I am using the simple current division rule, the opposite resistance divided by the opposite resistance plus the common resistance or the current flow resistance path, which is RL and RF. Okay, so just by using all of these components, one could end up having this relation. So now that we are going to do some small bit of approximations here, as stated, if the value of RID is much larger than the resistance of RS and RF, as well as the value of RO2 is much larger than the resistance value of RF and RL, one could approximate these expressions. So what I try to say here is that over here one would end up, yeah, so over here one would end up having this particular ratio as 1, just because the RID value is quite larger, so due to which this entire ratio can be considered as 1, and similarly uh, one would consider this ratio as also to be 1, just because the value of RO2 is much larger than the other impedances. So approximately these ratios can be approximated to 1 and 1, so that the total open loop gain that we have could be returned as approximately equal to A1 times that of GM2. Okay, so hope I have not confused you people. And now that we just need to find the input and output impedance of out of this A network. So that is RIF, the input resistance of basic amplifier. Okay, yeah. So now one could visualize from here that the input impedance is nothing but the series combination of all these three resistances. So I could write it as RS, RID, sorry, plus the RF. Okay, so this is what we have, and the output impedance again. In order to identify the output impedance, as I said, we will be pumping in a current, and then trying to kill the independent source. So let us try to do that with this particular picture, or let me just copy this and then put it here. Okay. So the very first step that one has to do is to kill this input source Vi. So which means that when I try to short this particular node to the ground, it becomes absolutely 0. So we have this Vi that is made as 0, and due to which what happens is that the Vid becomes 0. So when a Vid becomes 0, this voltage controlled voltage source will also become 0. So what it really means is that everything becomes 0, and since because here we have a current source, having a current source being equal to 0 is by making this a open circuit, right. So this becomes a open circuit, this current source will then become a open circuit here. Now based on this, we end up having a structure which is composed of these resistances. Okay, so now I have this RO2, and then there is a kind of connection of RL and then RF, and the tail end of this RF is connected to the ground, and even this R0 is also connected to the ground. It means that they are being shorted. Okay, so now that in order to find the impedance through this loop, we have to pump in a current of Ix and then measure the drop across them. Okay, so it's a pretty simple process. The drop across this this current source Ix will give us the value of this total impedance, right. So basically Vx is written as Ix times that of Ro2, because the current has no other path to leave out, so it has to loop through this Rf and Rl. So what I really mean is that the Ro is nothing but Ro2 Rf as well as Rl. Okay, so now that we got the output impedance of the basic amplifier, and now let us try to compute the feedback gain and then the feedback input and the feedback output. Again the feedback input and the feedback output excluding the source resistance and the load. Okay, so these are the 5 different terms that we need to find. The way that we always find out this particular term is by knowing that the output is a current, but the input is a voltage source Vs, and it can be always written as 1 plus uh, like A divided by 1 plus A beta, and the RIF and ROF, as we know that they are making a series connection, this can be written as something like, okay, and in the computation of this we need to exclude the resistance Rs, and from ROF we have to exclude the impedance of RL. Okay, so hope that you are clear right now. So with this let me end the stream, and you can just join the yeah, the WebEx right now.